One other phenomenon is called thin film interference. It's slightly different than some of the other rainbow effects you've seen. This is really caused by the difference between two media, but it goes into something called in phase and out of phase. A lot of students find this very, very challenging for some reason, and it really isn't something that you can just memorize a formula. You kind of got to look at the situation individually. So I'm just going to illustrate that with an example here. Now, if you recall some of the things about basic waves here in terms of reflection and transmission, I'm going to make this being a boundary between two media. Okay, and I'm just going to make up things and saying it's coming from air into some other substance. I'm just going to make it a 2 here. Okay, so this is index of refraction of 1 and index of refraction of 2. And suppose a wave came in here, and I'm just maybe make a different color here. Here comes a wave, and it comes in like this. Well, what's going to happen is part of it is going to reflect. So some of it's going to reflect, and some of it's going to get transmitted. And the part that gets transmitted will get bent towards the normal because it goes again a little slower here towards the normal. Now, it's going to hit another barrier. It could be even the tabletop, okay? But it's going to hit something else here. Now, when it hits this, I'm going to just say here that this n is equal to 3. In other words, you have n equal 1, n equal 2, and n equal 3. Just 3 separate media. This is maybe perhaps what it looks like. I don't know. This is another layer of something. What would happen here? Again, some of it would get transmitted, but also some of it's going to get reflected. Now I'm going to deal with the reflected part. Okay, and it might look something like this. The reason I'm dealing with this is because you have to think about what just happened here. Okay, again, transmitted, reflected. Part of it will get transmitted and reflected. We're going to ignore the transmitted part for this third one. We don't really actually care about it, only these two. Now, if you look at what's happened here, when it hit this one, because it hit a more, I'm going to quote unquote, rigid medium, this part actually gets reflected. And if you remember, if a wave came upright, it's going to come back inverted. Okay? We call that a 180-degree phase shift. If it goes upright and it comes back upright, if it comes back on the same side, we call that a 0 degrees phase shift. So keep that in mind. What happened here? Well, it hit a more rigid medium. That would get reflected. So the reflected ray right here would be shifted 180 degrees. In other words, it's flipped. The transmitted, well, the transmitted always stays on the same side. So this would still be the exact same phase shift or phase as this. It would be in phase. Here it hit a more rigid medium. So here again, it got 180 degree, and because it got transmitted, it's still another 180 degree phase shift. Now notice it. Seeing my picture here, you can see that both of these waves are actually in phase. The reason being is because one of these got flipped, but this one got flipped. And so in fact, these are going to meet up at exactly the same thing and have what's called constructive interference. Only if the path that it went, and here's the path that goes down and then up, is a multiple of one wavelength. Let me write that down. In other words, you'll get constructive interference, okay, if it's a multiple of a wavelength. Okay, and the path length here, well, I'm going to call this thickness T. That's the thickness of this second medium. That's where it traveled through. In other words, if this path here was one wavelength, then they're going to meet up in phase because they both flipped. And how to deal with that is, well, this went 1T and another T. This went 2T. This, in this situation, is for constructive interference. In other words, they're going to add up. If I want a destructive interference, I would like this to be a half a wavelength. Okay, I would like it to be a half a wavelength. So in other words, 2T I would want to be equal to, well, I'm going to write n plus a half lambda. This avoids any multiple integers. In other words, 1, 2, 3. It only makes it 1.5, 2.5, where n is equal to 1, 2, 3, etc. Okay, and you end up getting, so this would be for destructive. Okay, that's for destructive. Students get confused by this and they want to memorize these two formulas. They're like, well, okay, this is constructive and this is destructive. I get it. It depends on the situation, though. Let me give you another example where this will actually change. Okay, if this is for this example. Now imagine you had like a soap bubble, and this is where, like, you know, you have a soap bubble here, and I'm going to make here n is equal to 1. Let's say the soap is like n equal to 1.4, And underneath there is a pocket of air again, and there's n equal 1. So it's soap bubble sitting on some desktop. Air, soap, air. Same thing again. Here comes a wave, comes along. Some of it gets reflected. Well, it went off a more dense. There's a 180-degree phase shift. Transmitted, keeps going, reflects again. Now this reflection is off a less dense medium. In fact, this will still be in phase. Then it gets transmitted. In fact, this will be a 0-degree phase shift. Notice the difference between these two scenarios. These both flipped. Only one of these flipped. Now it changes the situation. If the distance is only a multiple of a wavelength, this will actually result in destructive interference. So this equation will be destructive interference. If it's a multiple of a half a wavelength, now these will end up becoming shifted by a half a wavelength, which means they'll suddenly be in phase. And this would be constructive interference. It depends on the scenario. This can be constructive or destructive, and same with this, but it depends on the scenario. You might want to make use of these equations because often on the AP exam they'll mention minimum thickness besides 0, in which case this will be a 1, and this could be a 0 right here, which will give you only a half a wavelength shift. It depends on the situation. But be aware here of the differences between these two.